Okay, so we stopped at this geometric distribution. So the main difference is we do not allow the replacements. So in the case of binomial one, we think about the infinite number of balls where we have a fixed ratio between the, for example, red balls or white balls. But in the case of this no replacement case, we are actually reducing the total number of balls in the basket. So every time you pick one ball, it will affect the next probability. Okay, and then also we will learn a few more probability distribution, but there are a few things that you have to keep in mind. So distribution is represented in this form. So it is having a name of a hypergeometric. So we use the first letter H. So that's the distribution name. But what I wanted to note is that we have a few letters inside of the parentheses, and also in this parentheses we have the two parts. The first part is this X, and then the second part is involving some other letters. So here, separated by this semicolon, in the left side, they represent our random variable, and then the right hand side is containing those parameter values. So here in this case, X can be random. X is random variable, so it can be chosen different values that we basically pick up from our distribution. But at the same time, that distribution has a parameter of these large n, and small k. So if you think about the Gaussian distribution or the normal distribution that you're familiar with, and then in order to, we kind of know the general shape of the Gaussian distribution, but in order to exactly draw the shape of the distribution, you have to know what the mean is and the variance is. So you have to basically you have to obtain the information about the mean and the variance value. So those two values are the parameters that specifies the exact normal or Gaussian distribution. So you can think of those values, large n, small k, on the right side of this semicolon, right? So you can think of those values as those parameter values that help you exactly specify the distribution. But in general, in this case, the distribution has a particular class. So we know this distribution is called this hypergeometric distribution. So it is definitely different from normal distribution, right? So this hypergeometric distribution has a certain shape, but that shape is parameterized with these parameter values. So in this case, so let me just remind what we learned about this hypergeometric distribution. So in order to specify the exact details about this hypergeometric distribution, we need a 3 number, and then n is the total number of balls. Okay, and then k is, so suppose we have red ball and the white ball. And then this number of k, so suppose n was like 1,000, and then k was actually telling us the number of the total number of red balls. So suppose that was 700. Okay, so this is red, and this is 700. Okay, and then also the last parameter n, which is a small n, is actually the number of the samples that we obtain. So how many samples or how many balls that we choose from our basket. So that number is represented as this small n. So this small n should be definitely smaller than the total number of balls, of course, right? So it can be like 50 or maybe 900 and so on. Okay? So in this case, so those are the parameter values that specifies our the details of this hypergeometric distribution. But what is our random variable? So what is the meaning of the random variable that we have? So x, which is located in the left side of this semicolon, this is basically the number of red balls out of n selected samples. Okay? So we are basically computing the probability of an x. So let's use this h. Okay? So h of x being, for example, like 30 out of 50. Okay? In this case, we use n being 1,000, k being 700, and n being 50. So in this case, what we have to know or understand about this probability distribution is that we have to compute. We have to know how to compute the probability in this specific case, and that specific case can be computed in this form. So we choose 50 balls out of 1,000 balls, right? So this is all the possible number of different set of samples. I mean the 50 samples, and then this out of 50. No. In this case, the meaning of x being 30 means we have to sample 30 red balls out of 50, and at the same time 20 white balls out of this 50 number of samples. So in this case, we can compute the total different cases as this guy. So it is, yeah. It should be, so we have 70 balls in total, 70 red balls in total, and then we have to select 30 of them, right? And then at the same time, we have 300 white balls, and at the same time, we have to have like 20 white balls, right? And then we have 30 balls of red balls, and so the probability of having this, let's see. No, here in this case, we do not think about the probability. So these are the total different number of cases of selecting 30 red balls out of 700 total red balls and 300 total white balls. We select 20 white balls. So these are the probability of x being 30. So that's how we define this hypergeometric distribution. Okay, so in this case, mu and the sigma squared, which are the mean value and the standard deviation or the variance of this hypergeometric distribution, is defined in this form. So basically, x is our variable that can change its value, but n and k and small n are the parameter values that are fixed. Then the mu and the sigma squared can be computed in this form. So we are not learning, or we do not study how to derive or how to prove these equations. So you can kind of memorize them, but in order to help you understand how this one is correct a little bit, we can compare this with the binomial distribution. So the main difference between binomial and hypergeometric is that whether we do the replacement or not, right? So once we pick up one sample and then we put it back to the basket, and in that case, it is the same as the binomial distribution. But if we do not replace, or we do not put the picked ball into the basket again, if we do not do so, then we call that as a hypergeometric distribution. And then in this hypergeometric distribution, if we have really large number of total balls in our basket, and also if we have a relatively smaller number of samples, and then whether we replace or not, it will not affect the total probability or the behavior of these probabilities. So in these cases, we can kind of compare between these two cases of binomial and a hypergeometric distribution. So in the case of a binomial distribution, we learned the mean is represented as this, n times p. And then here, if we compare it with that, and n, it can be represented as n times large k over large n. So n over large k over large n can be viewed as approximately as p, because we have 1,000 balls, which is 1,000 here in this case, and k is 700, right? 700 is the total number of red balls. So this probability value was used as this p in the binomial case, right? So in the case of binomial, what is the probability of sampling the red balls at each trial? So that was the meaning of the probability p in the Bernoulli distribution, right? So that way, these are approximately the same. And then here in this variance case, so we had a variance of an npq. So n is here, and let's ignore this first part, okay? And then after then, we see n, and this one is chiral p, and this one is chiral q, because it's 1 minus p, right? So that way, it can be viewed n times p times q, which is the same as binomial distribution, but we see additionally like this, the left part. And let me change the color. So here in this case, as I mentioned, we kind of assume that n, which is our actual sample size, is much smaller than the total number of balls that we have in our basket. So that's when those binomial and hypergeometry are the same. So in this specific case, so it can the numerator can be approximately viewed as just an n, because a small n is really small. So it is just becoming as n over n minus 1. So if n is also really large, okay, and then n minus 1 and n will be approximately the same. So it will converge to 1. So that way, if n is really large and small n is much smaller than capital N, then this hypergeometric distribution becomes the binomial distribution. Okay, that's it for this hypergeometric distribution. Okay, and then one thing that I missed. I'm gonna cover the one thing that I missed in the last class. So one student asked at the end of the last class about the multinomial distribution. So we go back to Bernoulli and binomial distribution. Okay, so binomial distribution is basically the sum of Bernoulli distribution, right? So we independently sample or perform this Bernoulli random variable thing, and then we basically sum up with a certain number of trials, right? So then it becomes binomial distribution. So if we think about the Bernoulli distribution or Bernoulli random variable, we assume that there are only two different cases, either 1 or 0, and it has its own probability associated, right? So x, in the case of Bernoulli distribution, x can be 0 or 1, and then this has the probability of 0.3, and this one has the probability of 0.7, and then we call that as p, right? But we can extend this Bernoulli random variable into multinolly random variable, where we have not only just 0 or 1, we can have 2, 3, 4, and so on. So in this case, instead of just a binary one, we extended it to have multiple variables, multiple different values, and then the probability is still distributed over all the possible event outcomes that we have. And so it can be it can have the probability of 0.1, 0.2, 0.1 again, and then 0.3, and then what is the total? Let's see, 0.3, right? So in this case, this is again a multi-nodal distribution. So you pick up one value or one random variable out of these possible values, and then each of them has its own probability value. Okay. In this case, we can also extend this guy into multinomial distribution, just like we extended Bernoulli into binomial distribution. So suppose we do this kind of a sampling with maybe 20 times. Okay, so we fix the total number of samples as 20. And then here in this case, in the case of binomial distribution, we basically considered the number of ones out of 20 samples. Okay, so if we had 14 ones, and then it is the same as, it is at the same time means we have let's see, 6 0 out of 20. So we fixed this 20, right? And then in this case, we see 14 ones and 6 zeros. But in this case of a multi-nodal distribution, so let's fix n as 20. But in this case, we basically think about the count of 1, 2, 3, 4, 0, 1, 2, 3, 4. So in this case, suppose we observed our random variable of a multi-nodal distribution as this. So as the number of count or occurrences of 0, we observed maybe 3 zeros, and then maybe 2 ones, and then 5 2, and then 6 3, and 4 4s. So in these cases, the total number will still be 20. Okay? So these are one particular outcome or one example that we can consider as event outcome out of our event space. Okay? So how can we define or how can we think about our event space? So our event space is now becoming a vector. So in the previous case, we only considered the scalar random variable, but as we learned in the previous chapters, our event space, each event outcome can have multiple different random variable x and y, and then we think about the pair of these values. So in this case, we see we view this random variable, for example, y, as 5-dimensional vector, where the first one is the number of zeros that we observe. So this is one example of our random variable, or event outcome. Okay. So all these 5-dimensional vectors are forming our event space, but at the same time, these vectors are not in the real value domain. They should be integer, and then also we have to have an additional constraint of their total sum should be 20, right? And then also each of these values should be non-negative, so they cannot be negative because they are just a count or the number of occurrences. So in this case, we call that as a multinomial distribution. So so in this case, so suppose we want to let's just compute the probability of observing this random variable, this specific random variable value as our multinomial from our multinomial random variable. So P, or the probability of y being this, can be computed in this form. So we see 3 zeros. So the probability of seeing 0 in one trial is just 0.1. So we are just multiplying like this, then 0.2, to the power of 2, and point 1 to the power of 5, and point 3 power of 6, and 3 power of 4, right? So this is one specific example, but we have to consider the different combinations. So in terms of their orders, we might observe 0, 0, 0 and 1, 1 and so on. But at the same time, we can observe 1, 0, 0, 0, 0, 1, 1. So these are just an example of considering those only the two. So this one is just one example, but the 0, 1, 0, 1, 0. So this is another another sequence that generates the same random variable of this y value or y vector. So we have to consider all these different possible cases. So how many cases do we have? So it is written as this: 20, then 3, 2, 4, 5, 6, 4. So yeah, so this one is this. So out of 20, what is the different number of cases of sampling? 3 zeros and 2 ones and 5 twos and so on. So in this case, similar to so the case of 20 combination 3, so we can compute this guy into this form, right? So similarly, this can be computed in this form. So 20, then like this, okay? In this case, it should be this, right? So similarly, we can extend this guy, which is a different, the partitioning, not just into 2, but into multiple groups, where we have 5 different groups. And so in this case, we can compute the different orders as this guy, okay? So these ones are the total number of different cases or different orders that generates the same count of each of these 0, 1, 2, 3, 4, 5. Okay? Okay, so this, so let me give you one practical example of utilizing this multinomial. So one representative example is called this topic modeling. So I think I mentioned about this maybe in some of the previous lecture. Yeah. So this is one research paper, but it's been cited 1,000 times. Okay. But anyway, so in this case, it's exactly utilizing the multinomial distribution when we model or when we analyze some text data. Okay, so in this case, we are starting with a few of these topics. So it's a little unclear to see, but on the left part, so they are showing multiple different topics. So you can think of each of these rectangles as one multinodal distribution, and that multinodal distribution is specified into this. So here in this case, in the previous my example, 0, 1, 2, 3, 4 was possible different outcomes, but in this case, since we are considering the text data, each outcome is each different keyword or the term, and then it has its own associated probability. So the probability of picking up this the word gene is like a 4%, and DNA is 2%, and genetic is 1%. And then suppose we have a different multinodal distribution. Okay, that multinodal distribution has a different keyword and its associated probability. So in this multinodal distribution, we have life associated with the 0.2% probability, and so on. Okay. So if we look at this, each of these topics or each of these multi-nolly distribution, and then it has a kind of a meaning where those keywords that have a high probability value are actually contributing to the meaning of this topic. So although these probability look quite small, but all the possible different keywords are so many. So like a 4% of probability is probably the most significant or the biggest probability value among these multi-nolly distribution. So it's kind of a sorted version in terms of the decreasing order of the probability. So the gene has the most probability, and then DNA is has the second most probability, and so on. So as we can see, this kind of multi-nolly distribution is kind of representing the topic of maybe biology or related topics. And this kind of thing, let's see. The third one is about like a neuron and brain and things like that. So it's representing a different topic. So here in this case of topic modeling, we consider a different multi-nolly distribution where each of multi-nolly distribution is representing one specific topic, whether it's a science or sports or this type of DNA or biology related topics and so on. So we consider multiple different multi-nolly distribution, and then our document. So suppose you read one news article from Naver, for example, in the morning today, and then that document can be viewed as a sequence of each word, and this each word is actually sampled from a particular topic. So if that news article was like a biology topic, okay, and that biology topic, I mean, each term was actually sampled from this yellow multi-nolly distribution, okay, and then one document was sampled from this biology topic, and then one document can be viewed as kind of a multi-nolly random variable by just considering the count of each word that we see from our document. So in the news article that we saw early in the morning, that article had three occurrences of keyword gene, and 2 occurrences of DNA, and then 5 occurrences of genetic. And then we can compute the probability of generating that document or that multinomial random variable sample, just like this, okay, from the biology multi-nolly distribution. Okay, so if our document contains more words that are mainly appearing in these top-ranked keywords, and then the probability of generating that document from this multi-nolly distribution will be much higher than generating that multinomial document random variable from other topic. Okay, so we can compute the probability of generating our document from this topic, and starting from this topic, we can compute the probability of generating the same document, and then we can kind of compare the probability of generating our document from this topic or this topic. In other words, this multi-nolly distribution or this multi-nolly distribution. Okay, so that way we can kind of infer, or we can kind of estimate which topic our document was generated from. So that is the main idea of this topic modeling, and then that's one practical and useful example of utilizing this multi-nolly and multinomial distribution. Okay, so now we learn about this negative binomial. I don't know why it is called negative binomial. Let's see. So here in this negative binomial, the meaning of this is, so it doesn't have much detail, but So we don't have much time. So yeah, let me briefly explain and then continue next time. So negative binomial means, so we know the binomial distribution, right? And here in this binomial distribution, we represent it as this. So B of, so let's use this guy. So we represent binomial distribution as this, B of x, and then the necessary parameter is n comma p. So n is the total number of samples that we have to obtain, and then p is the probability of sampling, for example, red balls at each trial. And then our random variable that can actually vary, that can change, is this number of red balls that we observe out of n total number of samples. Okay, but in this case, the negative binomial, I don't know why it is called the negative, but it's actually kind of an inverse or reversed binomial distribution. So in the case of a negative binomial distribution, we actually change the role of random variable and one of the parameter that we have. So in this case, so let's call that as negative binomial as NB, and then we actually change those two, n comma x comma p. Okay, so in this case, so we can imagine the same process of a binomial distribution. So we basically sample a ball independently, and then the probability of sampling the red ball is fixed as p, for example, like a 70%. So this is a fixed parameter. But in this case, where we change it the role of x and n, so we fixed, it means we fixed x, right? So x is fixed. And what was the meaning of an x? So x was the number of balls, the number of red balls that we have to obtain out of n samples, right? So in this case, suppose we obtained 50 samples, and then out of these 50 samples, the specifically example x was 30 red balls. But here in this case, we fix x. So we have to obtain 30 red balls. Okay, so that is the fixed situation. So that is our assumption, because that is working as the parameter value. Okay, but here we consider different possible values of an n, the total number of samples, in order to obtain 30 red balls. Okay, so so let's consider the probability of n being, for example, 30. Okay, so in this case, p was 70. So in this case, what it means is that we have to have a 30 red balls, but we consider the probability of the total number of samples being 30. Okay, so in this case, it means, so the total number of samples are 30, and then the red balls are 30. So every ball that we sample should be the red balls. So in this case, the probability will be the 0.7 to the power of 30. But what about n being 29? So can we sample 30 red balls out of 29 total sampled balls? It is never possible, right? So of course, in this case, the probability will be 0. And then what about the n being 31? So in this case, so we have to exactly sample 30 red balls at the total number of 31 samples. So it means, so we have to sample 31 red balls, I mean the 31 balls, but at the last position of 31st trial, we have to select a red ball, right? And then previously, in the 30 trials, we have to sample 29 red balls, because we know at the last position we have to sample this red ball, because that actually satisfies this condition of n being 31. Okay, So if we already sampled 30 red balls, less than 31 trials, and then n will become 30, for example. So n will no longer be 31. So in this case, we can think about the probability as this. So let me have just 1 minute. So here in this case, the last one should be a red ball, and so red ball, the probability of sampling a red ball is 0.7. And then out of 30 previous samples, we have to have 29 red balls. So 0.7 to the power of 29, and then 1 white balls, 0.3. Okay, and then we consider all the possible different sequences, and that sequence is changing here. So here in this case, we have 30 possible positions, and then out of these 30 possible positions, we have to choose 29 red balls positions. So all the different number of this combination value will be different sample, different number of cases. So this is actually the probability of n being 31 when x is fixed as 30 and p being 0.7. So in this way, we can compute this negative binomial cases. So basically, we understood how we compute the negative binomial cases of a random variable, and then basically the main difference, or how we understand this negative binomial, is from changing the parameter and also the random variable. Okay, so which ones are fixed, which ones are our variables are actually changing. Okay, so that's it for today. So yeah, thank you very much for the homework, and then let's see you next time. 네. 중앙고사요? 10월 말일인 거죠. 10월 말쯤 되는 거죠.
10월 20일쯤 알고 있는데 그때 보나요? 아니면
그때 아마 그 시험 기간 동안에 월요일 날에 아마 보려고 해요. 네. 네.
뭐가
네.
31시 30이 아닌 이유가 뭐예요?
31시 30이 아닌 이유가요. 그러니까 여기서 주의해야 될 거는, 내가 30개 레드볼을 뽑기 위해서 31번의 트라이얼이 필요했다라는 말이요. 31번째는 무조건 레드볼을 뽑았어야 돼요. 그러니까 31번째 정확하게 레드볼을 뽑아서 30개 레드볼을 만족을 했었어야지 되는 거예요.
네네.
그렇지 않으면, 그러니까 그냥 뭐 예를 들어서,
그러니까 이게 만약에
네,
이게 여기가 다 레드면
네, 그렇죠. 이거는
여기서 다 끝나는 거니까.
그렇죠. x가 30이 되는 거예요. 네. 31이 더 이상 안 돼요.
횟수가 31번 돌아가는 게 아니니까.
그렇죠.
네. 감사합니다.
그리고 제가 이거 그래프를 표를 사용해서 그렸는데, 이게 히스토그램 그릴 때 보통 폭을 다 똑같이 하잖아요.
네.
이게 보니까 글자의 글자 너비만큼만 되더라고요. 그래서 혹시 이거를 똑같이 맞출 수 있는 방법이 있나요?
테이블로 해주면, 이거는요, 여기다가 이렇게 설정을 해갖고 이게 너비를 다 세팅할 수가 있어요. 그래갖고 여기서도 또 하고 여기서도 또 하면 돼요. 야, 근데 이거 대단하죠? 네.
제가 문과에서 교차점에서 들어오는데 그러다 보니까 미적분이 나오더라고요.
네.
모르는 부분이 나와서
네.
혹시 그 해야 되는 부분이 지금 다 통째로 할 수는 없잖아요, 이과 수학을 지금. 그래서 어느 뭐 찍어서 시험 때 계산 문제 많이 나시나요? 그러니까 이번에 과제 계산 문제 너무 많아가지고.
이거 연습 문제가 다 계산 문제들이더라고요.
네.
이게 사실
네.
그냥 이 probability distribution이 이런 의미를 갖고 있고, 이게 어떤 애플리케이션에서 이렇게 사용될 수 있다라는 거가 포인트였어요, 사실. 그래서 이제 그런 그러니까 좀 이그젠플에 해당하는 계산 문제들이 좀 많이 있었던 건데, 시험이 어떻게 나오느냐에 대한 질문은 아마 그런 질문을 피할 수는 없을 것 같긴 해요.
그래서 감사합니다.
미적분을 안 배웠다고요?
미적분을 하긴 했는데 제가 배운 건 다항 함수밖에 안 배웠거든요.
네, 오케이. 그러면 뭐 초월함수나 뭐 사인, 코사인, 뭐 EX, 글쎄요. 어떻게 해야 되지?
어느 순간에 제가 뭐 다항 함수는 없고 지금.
네. 모르겠네요.
아 예.
나도 잘 모르겠어요. 아직 시험 문제를 아직 나도 내거나 생각할지를 아직 많이 안 와서.
네.
근데 뭐 하여튼
네.
만약에 시험 그걸 한다면
네.
연습 문제를 사실 싹 다 풀면은 되는 거거든요. 싹 다 풀 줄 알면 되는 거여서
네.
네, 그렇게 준비를 하고 거기서 필요로 하는 어떤 초랑수의 적분이 나왔거나 그러면 그거를 좀 공부를 하거나 적분량 알려주거나.
네. 감사합니다.
근데 여쭤볼게
네.
여기서
네.
그냥
네.
31C 30하고 그 0.7에 30 그다음에
네.
0 그게 무슨 차이예요 이거하고?
아 그러니까 그거는요. 그러니까 여기서 31번째 만에 30개의 볼을 뽑았다는 거는 이전 30번에서 다 레드볼을 뽑아버리면
네.
이거를 더 이상 할 수가 없는 게 돼버려요. 왜냐하면 30번 만에 30개의 볼을 이미 30개의 레드볼을 뽑은 셈이 되니까 그 경우는 n이 31이 되지를 못해요. 그 경우는 n이
근데
30이 되겠죠.
이게 저희가
네.
제일 처음 할 때 N31 이렇게 했을 때 그
네.
뜻이 31번 뽑았을 때
네.
레드볼이 30번 뽑힌다는 의미 아니에요?
맞아요. 그건 맞는데,
네.
이제는 우리가 30개 레드볼을 이제 무조건 뽑아야 되고,
네.
n이 정확하게 31번째일 확률을 구해야 되는 거잖아요. 그러면 지금 레드볼만 다 30번을 뽑고, 그 다음에 뭐 화이트볼을 이런 식으로 뽑아갖고,
네.
이렇게 31번에 트라이얼을 했다라고 치면,
네.
이거는 n이 얼마여야 되느냐? 이 케이스는 n이 30인 쪽으로 프로바빌리티가 할당이 되어야지 돼요. 왜냐하면 이거는 이게 몇 번째 만에 레드볼 30개를 뽑았냐? 30번째 만에 뽑은 거니까 31번째 뽑은 게 아니고.
그러니까 이거는 여기 안에 포함돼야 된다고요?
그렇죠. 네. 네. 그래서 n이 31번째 이 확률을 구하려면 최소한 마지막에 레드볼을 끝에는 맞춰야 돼요. 그래서 이거를 마지막으로 픽스를 고정을 이렇게 한 거예요.
그러니까 이게 이렇게 써줬을 때 그 의미 안에
네.
이게 다 포함이 돼 있다는 거네요.
그렇죠.
마지막에 이렇게 있어야 된다.
더도 덜도 말고 정확하게 31번째에
아,
그 뜻이에요.
딱 그 뜻이구나.
네.
이게 31번째.
네.
이게 사실
네.
확성에서 그게 무조건이 도구로 쓰이는 거지 핵심 부분은 아니잖아요.
네. 네.
그거 좀 도구로 좀 제한하시면
내가 그러면 뭐 필요하면 그 초랑수의 정보를 내가 알려줄게요. 칠판 써주거나 시험 볼 때 필요한 그런 것들은 공식처럼 내가 제공을 해줄게요.
딱 나가시는데.
졸게